Hi everybody, welcome to class today. Hope you all are doing good. I got a little bit of a headache, so kind of gonna go to a slow start here. So yeah. Um, Today we're gonna be talking about pointers. So that's gonna be the topic of the day and dynamic memory allocation. And hopefully we get through it. So we shall see. I hope you all are doing good. So let's get to it then. Actually, let's keep the chat. No, it's just a headache. Like sensitivity to light kind of headache too. I don't know. I took a pill at exactly 4:30 p.m. and it says it takes place in 30 minutes. I took Advil, so that will be exactly now. So hopefully within the next 5 to 10 minutes it kicks in. I don't usually get headaches, unfortunately. So I'm sorry about you getting some of those. And because I don't usually get them, it's when I get them it feels very strong. So yeah. Um. Anyways, we'll get through this. And if worst case scenario, if it gets bad, I'll just like end early or something. But I mean it should kick in soon. So okay. So first of all, let me define what a pointer variable is. And I'm just going to copy this definition from the book, and I'll talk about it. I should say therefore. And is therefore set to point to a memory address. Therefore set to point to a memory address. Okay. Thank you for the nice messages. Okay. So what is a pointer variable? A variable whose content is an address. So normally, when you have a variable, it's called variable because it varies, right? You can change what's in it. Otherwise, it's a constant. And what it is, it's somewhere in memory, you're keeping some data, and that data can change. Now, that data can be a lot of things. It can be integers, floats, whatever. Ultimately, it's represented as bits, zeros, and ones, but you give the meaning to that. You know, you use the ASCII table. You make it become from numbers to characters. You give it floating point notation, like the way that floating points are kept, and now it becomes a decimal. You can just flat out do an integer. You can also create classes with this, right? And classes are made up of their own little variables too. So you can do a lot of things with it. And one of the things that we haven't talked about yet in 135 or 202 is that you can keep also addresses themselves, because somewhere in memory this variable is kept, and the way that it decides where to keep it is the operating system tells your program, like, hey, what do you need? And the program's like, I need to store an integer, and the operating system's like, okay, in my land an integer is 4 bytes. Could be 8 bytes somewhere else, but here it's 4 bytes. So I'm going to assign to you 4 bytes of the memory that I have. And you can think of the memory as a big plot of land. And somewhere in there, they're going to allocate you 4 bytes. You need to know where that is in the land, right? So you get an address, like a physical address. And that's exactly the same thing in memory. You get a physical address. The difference being, normally, where I live, I have a number, and then I have a street name, right? And then you have a city name, state name, and zip code. When it comes to an address in a computer, we don't need to make it that complicated. We just make it a number, kind of like a phone number. You know, it's just a single number, and it's unique. Nobody else has the same number. Theoretically, nobody else has the same address either, because at least the zip code would change, or the country would change. So, anyways, that's essentially when I'm talking about an address in a computer, what I mean. It is an address in memory, and that address is kept in hexadecimal code. Now, what is hexadecimal code? Normally, when we think of numbers in like the human race as general, we think of the numbers 0 through 9, right? And that is called the decimal system because it has 10 digits in it. 0 through 9, that's 10 digits, because we don't consider 10 to be one of them, because 10 is just made up of 2 digits that we already have, 0 and 1. So we have 10 different symbols that represent numbers, right? We have this little thing that looks like a circle, this thing that looks like a stick, this thing that just looks like a stick that got twisted, and then this looks kind of like a squiggly stick, and then this one's just a bunch of sticks together, stick and a half a circle within a circle, 2 sticks, or 3 I guess, 2 circles basically next to each other, a circle and a stick, and that's pretty much what this means. But you know, we don't call them sticks and circles, we call them 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? That's what we call these numbers. We've assigned these symbols to represent this numerical system. But I could have just as easily said that I'm going to say that instead of the one being represented by a stick, it's represented by a star, you know? Or I could represent it by that, whatever that is, I don't know, like that, you know? Or it could be represented by a triangle, actually, you know? And a 3 could be represented by a square. And a 6 could be represented by a diamond. The 4, I could flip it around and do like an H. You know, the point is that we as a society, Western society, because they have different symbols in different societies, I think it's Western. Could be, actually, I believe this comes from the Arabic system. That's when they come up with numbers, although the 0 comes from the Aztecs, I think. And so, you know, in general nowadays, Arabic, nowadays they basically the whole world has adopted it for the most part, that the numbers, symbols that we're going to use are these guys, right? And it works because it's a base of 10. Now, there are smaller systems of numbers. So, for example, there's binary. In binary, you only need 2 symbols. And so it's convenient to just take those 2 symbols and basically adapt them to be binary, 0 and 1. So how do you represent basically 2 in binary? Well, you go ahead and do 1, 0. And that's it. That's 2. 0 would be 0, 0, 1, 1, 0, and then 3 would be 1, 1, and then 4 would be 1, 0, 0, and so on, right? So basically, in binary, you just need 2 symbols, and we choose to use 0 and 1. But you could just as easily choose a different symbol, right? Okay, so this works for like any number system that goes from basically, well, you need at least 2 digits. So I suppose the most basic is binary, because a unary system, like, actually, no, you can get away with a unary system. It just basically sticks, you know? Unary would be like, that's 1, that's 2, that's 3, that's 4, that's 5, and at some point, I see that, 0, 1, 2, 3, 4, 5, and then 6. Okay, so it's kind of weird because 0 is actually kind of a 1 there, but we need a way to represent the 0, and so yeah, that becomes kind of like the 0. That would be like a unary system, I suppose. As you can see, the numbers can become really big, or at least the number of digits required for a number. The higher the number system, the range, so like decimal has 10 digits, is the less numbers you need to represent a bigger number. Okay? 5 only had 4 sticks. That's right. That has to be the case, because how do I represent 0 in this system? Like, I can't just say that nothing here represents 0. That doesn't really work. So I have to use a stick to represent 0. So this is really the 0. 1, 2, 3, 4, 5. So I know what you're saying, it's missing a stick, but that's kind of what we need. We can't just say that blank is it means 0, because that would mean that blank is a symbol itself. Just like in binary, how 0 is actually a 0, because here we can afford that luxury. you know? Oh, I see what you're saying. Yes, that's the headache doing its thing. I'm sorry. At some point I screw things up badly. 3, so 5, so I don't know. You get what I'm saying. 3, 4, 5, 6, 7, 2, 4, 6, 2, 4, 6, 7. Yeah. Okay. Yes. Thank you. Now I see what you're saying. Thank you. Okay. So, hexadecimal. It says that we have some internet issues. Okay, it's back alive. So we might have had an internet hiccup there. But anyways, hexadecimal. Hexadecimal. And the reason I'm going over this is because you might not have taken CP 100 yet. So hexadecimal is base 16. Okay? Base 16 means that there are 16 symbols to represent numbers. Instead of with decimal there's 10, with hexadecimal there's 16 of them. And so what would that be represented like? Well, anything from 0 to 9 is still going to be using the same exact digits. So a 9 in hexadecimal will be a 9 in decimal. However, when you get like blah 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 8, 9, instead of doing 10 as you would in decimal, you are actually going to use a new symbol because there's 16 symbols. And the at this point we had to kind of decide, okay, what symbols are we going to use? And people in general just said, let's just use the letters of the alphabet. And, that we kind of got away with it. So it turns out that in hexadecimal, we use the letters A, B, C, D, E, and F. That represents basically 8, 9, 10, 11, 12, 13, 14, and 15. So we use those letters. Can be uppercase or lowercase, but I typically see uppercase. Actually, I don't know. I see lowercase. We'll see it in a second when we run some code. Actually, I think it's lowercase. I don't know. It's hard to remember right now. But yeah. So that's how you represent base 16, because you need 16 symbols. We just use the letters because it's convenient. And if there was some sort of whatever you call like base 20 number system, we would just use more letters. Now, what happens if we do a number system that requires more than just letters? Like more than the enough letters that we have, then I don't know. You can start putting, you can start using lowercase letters and uppercase letters, or just literally random symbols. I don't know. But that's not very useful for us. The only real systems that we use in computing are going to be binary, decimal, and hexadecimal. And so why am I talking about hexadecimal? Because the addressing system that your computer uses is in hexadecimal code. And the reason is because, as I was saying, the higher the base of your numbering system that you go, the less number of characters you're going to need, or symbols, to represent a bigger number. So whereas I had to use like a bunch of sticks to represent it in unary, in binary, if I want to represent a 3, I actually need 3 digits. I need a 1, a 0, and a 0. Whereas in decimal, I just need a 3. Whereas in hexadecimal, I still just need a 3. But now, suppose that I want to represent the number 20. I need 2 digits to represent it in decimal system. What about in binary? How do I represent that in binary? I don't know. It's somewhere around here. Let's see. So that would be 2 to the 1, 2, 3, 4, 5. 2 to the 5th power is 16. No. 2 to the 3rd is 8. 2 to the 4th is 16. So that'd be 32. So I think it would be 1 less digit. And maybe we make a bunch of 1s here. So something like that. Go ahead and binary tree. Yeah, you're right. I don't know why I did that. I apologize. I put 4 in binary. Okay, so let's just say if you wanted to do 4, then you would do this. Okay, now go ahead and find out for me what 20 is in binary, please. I can't do the math right now. But anyways, what I can try and do the math is for hexadecimal for that. 20 in hexadecimal would be a 1. And then it would be, well, 10 in hexadecimal is 16. So then 1 would be 17, 18, 19, and 20. So 4, 1, 4. Did you guys find out? 1, 0, 1, 0. Okay, so 1, 0, 1, 0, 0. Thank you. Okay, cool. So that would be how in binary what 20 would be. Whereas in decimal system, it would be 20, like as we know it. And in hexadecimal, it would be 1, 4. We don't call it 14 because it's technically not 14. We just call it 1, 4. Okay? It's misleading. I mean, you can, but it's misleading. Okay? So you have to be careful about that. And so, as you can see, you need 5 digits to represent it in binary, and then you need 2 digits in decimal and 2 digits in hexadecimal. But you can already see here that that we're still in a lower level. So if we were to try to represent something like 100 in decimal, we go into the 3-digit range. Whereas in hexadecimal, that's still going to be in the 2-digit range. How much is that going to be? Multiply 15 times 5, that's about 75, right? Yeah, 75. So times 6. So it would be around something like 6, 4 maybe? To find hexadecimal, you just divide by 16, right? Basically, every time that you divide by 16, you just increase this thing by 1. I don't think you can just flat out divide, but yes, the remainder, yes. If you do the remainder, then yes, you'd be okay. So basically, 16 divided by this is about, well, yeah, it would be at 95. So I think it's about this, 64. You guys, you can go on Google and figure it out. So check that out, how much 100 is in hexadecimal. I think it's around 64, but I might be off by like a little bit. But the point is that it's going to be a 2-digit number versus a 3-digit number. And so this helps out because, as you can see nowadays, we got a lot of memory. We got in the gigabyte levels. Now in gigabytes, they go, I don't know if you guys know this, so I might as well go over it. One bit is the smallest possible measurement, and that's just a 0 or a 1, okay? When you have 8 of these, 8 bits, so that could be a combination like this. So 2, 4, 5, 6, 7, 8. 2, 4, 6, 8, yeah. 64. Oh, it was 64? Nice. Yay. Okay, so we got it right then. Thanks. Cool. So yeah, so you can see then here that already when we get to 100 in this has 3 digits, but this has 2. So already here, it's 1 less character to keep track of, right? And in binary, that's going to be a pretty big number already. So yeah, I don't want to do that one in binary. It's going to at least add like 3 more digits to that thing. So yeah. So anyways, going back to how you represent, how you name the number of bytes you have. 8 bits, which is the 8 zeros or 1s, is also represented as 1 byte. Okay, and that's going to be your unit of measurement. So when we say that an integer takes 4 bytes in memory, we're saying that it takes 32 bits. But we don't say 32 bits, we say 4 bytes. And again, that's just basically 8 times 4, which is 32. Okay? Now, when you're talking about 1 byte, which again would be 8 bits, if you have 1,000 of these, 1,000 bytes, we call that basically 1 kilobyte. And then if you have 1,000 kilobytes, that becomes 1 megabyte. And that will be the same thing as saying 1 million bytes. The word mega is kind of coming from million and kilo from 1,000, like a kilometer. And then if you have 1,000 megabytes, that becomes 1 gigabyte, okay? Which would be the equivalent of having 1 billion bytes, or 8 billion bits, right? So this is a scam that people pull when they're selling you internet. When they're selling you the internet, they're not using bytes, they're using bits. So they're like, we're selling you gigablast, which is 100 gigabits, So when you hear that, you're like, wow, you know, they're putting it like this, GBPS lowercase, I think. That's bits. And so when you see that, you're like, oh, it must be 1 gigabyte. So I can, if a file is 10 gigabytes, you know, I can download it in 10 seconds. Not really, because these are gigabits. So if you really want to translate it into bytes, you got to divide this by 8. So what is, you know, let's switch it to megabits so it's easier to divide. So that would be 1000 megabits divided by 8. You know, just to round things out quicker, instead of dividing by 8, just do dividing by 10. That way you can just remove a 0. So really, your download speed is actually 100 megabytes. You know, and actually it's going to be more than that because you're dividing by 8. So the exact number would be, I think, 120. Whatever 1000 divided by 8 is, okay? Whatever that is. So yeah, so big scam, you know. But this has been the history since dial-up. Also, when they're selling you hard drives, the story gets kind of deeper into this, because I think the real trick is that it's not exactly 1000. You're going by powers of 2, and so in reality, you know, this. So let me switch gears here. So now this is the other scam for like hard drives and things like that. For hard drives, they'll tell you that you got 1 terabyte hard drive. Now, what is 1 terabyte? We didn't get there. Okay, if you got 1000 of these gigabytes, which would be 1 trillion bytes, that becomes 1 terabyte. For example, I just got, from courtesy of a 4 terabyte SSD. So yeah, yeah. So that's kind of cool. So anyways, that's what I'm using to record the lectures. So this 1 terabyte, you know, when they're selling it to you, I went ahead and I connected my terabyte and my 4 terabytes, and it gave me, here, I can screen share so you can see it. Big time scam. Only 3.63 terabytes, even though it's supposed to be a 4 terabyte SSD, you know? And I'm like, why am I getting scammed? You know, worse, you know, that's almost like half a terabyte lost. That's a lot of information, right? Well, it turns out that if you actually go in here and look at the space available, you know, you see it says free space, use space, capacity 4. So it's technically 4,000 bytes of capacity, which, yes, it would be 4 terabytes in the cleanest sense. But what it turns out is that when we're really considering bytes, we're using powers of 2. And so already when we're talking about a megabyte, that's actually more of like 1024 bytes. You know, it's actually going to be 1 kilobyte. And so, you know, if you multiply this times 2, you get 2048, and then 496. And then from there, you get 8,100, whatever 96 times 2 is. That would be 8,100 and, wow, why can't I do this math? 96 times 2, you just gotta subtract 4 from the final number. It should be 92. Yes, right? 96 plus 90. So you're saying 922? No, you got too many digits in there. I think you meant 8192. Yeah, so yeah, okay. The trick when you're doing math is you basically do 100 times 2 minus the remainder here, so that would be minus 8. But I don't know why I could not subtract 8 from 100. Like literally was stuck in my, I blinked a headache. Yeah, so anyways, this number, you know, that is actually the equivalent in theory of 8 kilobytes, right? And so that's actually how many bytes you would need to have 8 kilobytes. But when you get sold something, they actually just give you 8,000. So that's technically less than that because of the numbering system going in powers of 2 instead of actually just going numbers. So really, 1 megabyte is going to be 2 to the power of So 2 to the 10 is then 2 to the 24. And then 11, 12, 13, 14 would be 16, 32 would be 15, 64 would be 16, and then 17 would be 128. So that would mean we're dealing with 128 and then 2 zeros here. So we got to go a little further. So it's going to be something like 2 to the 20. Here, let me do it. This one I actually want to make sure I get right. 2 to the power of 30. Let's see how much 2 to the 32nd is. So that one is already in the. Okay, so 2 to the 32nd would be 4 gigabytes. So 2 to the 30th. Okay, there we go. So 2 to the 30th is 1. So let me copy this down, and then I'll explain it. So 2 to the 30 is equal to 1, 0, 7, 3, 7, 4, 1, 8, 2, 4. Okay? This is actually how much 1 gigabyte should be per our measuring system. But what you're really being sold, because they did it the way that we did it initially by just basically adding zeros, is this. Okay? So when they tell you, I'm selling you 1 gigabyte SSD, they're giving you this much. But in reality, if we wanted our computer to say that we actually have 1 gigabyte of data, it's actually 2 to the 30th number of bytes, which, as you can see, is just about 73 megabytes more of data. Okay? And so that's kind of what we're getting scammed out of, 73 megabytes. Of course, the higher you go, then this becomes a bigger discrepancy. So if we go up to, let's say 2 to the 40, so this is in, so let's see. We have to go all the way to 1,000. So we should add about 10 more. So about 2 to the 40, yeah. So 2 to the 40 is going to be perfect, yes. Well, that's 1 terabyte. So let's go ahead and do 2 to the 40. 1 would be 2 to the 42nd. Yes. So 2 to the 42nd power is 4, 3, 9, 8, 0, 4, 6, 0, 4, 6, 5. And it doesn't give you the exact number because it's using scientific notation, but there's probably more digits after this, okay? So it's apparently 12 digits, as it should be. So for now, we'll just put zeros here. But yeah, so let me make sure I got the right number of zeros. So this is in millions, this is billion, trillions. Okay, cool. So this is the number of bytes that in computer science we would consider to be 4 terabytes. However, when we get sold something, they're just going to give you 4,000 bytes because they're multiplying it the way that I showed you. So because of that, if we go back here to the settings, that number should be just about what it's here. So here you can see that this says 4,000 bytes. But if I ended up having more, I guess there's no way I can show you easily. But if I added here another 398, oh wait, no, here we can see it easily here. Let's subtract. It says we got about 363. Okay, so 363 is missing about 40, approximately under 40, but 400 gigabytes technically. And if you kind of see, I mean, the math is kind of bad, but you can see that this is about 4.3, you know, and this is about 400. So this is about, it's missing about 600 here. So if we want to calculate how much this is in powers of 2, we probably have to divide it by 8, or I don't know. Anyways, that's too much CPE for me. So yes. What else you guys say? So yeah. So there's a difference in terminology per se. Okay, because if you're considering the conversion to be, you know, 1,000 becomes 1 kilobyte, or if you're gonna say 2 to the 10 is 1 kilobyte. Okay, and yes, there's a way, like you said, between IB and just saying B, and then the uppercase B and lowercase b. I believe that I always get mixed up, that the lowercase b is bits and the uppercase b is supposed to be bytes, but I'm not 100% sure on that. But anyways, the whole idea is that they do this very intentionally to try to basically lie to you. And it's not so shady anymore. It's just a standard nowadays. So it's like they're all just in the thing. So anyways, so this is a big sort of little sidetrack, but I think it's kind of important because a lot of you might not have taken CPE. So if when I say something like a gigabyte, you know, you might not know what it is, you know, and that's okay. So now you do, at least a little bit, at the introductory level. So how do we represent a hexadecimal address in the computer? We use the digits 0 through 9 and then letters A through F. But to make things easier for the user, whenever you print out an address in the computer, it'll put a 0 and an X in front of the hexadecimal value. So it could be something like 100 A B C. Okay, and then that would be the equivalent of that address. It could also be something like 010. That's address not 10, well technically 10 in both decimal and hex, but actually, oh no, that would not be 10 if it was in hex. Actually, that would be 16, address 16. Yeah, because that is 10 is 16 in decimal, right? Because you go all the way from to 0 to 9, A, B, C, D, E, F, and then from F you become 1. So you go A, B, C, D, E, F, 1, and then you go 1, 1, and so on until you get to 1F, and then you get to 2, 0, right? So that's the sign when you're printing out addresses that it's a hexadecimal address, which you'll see a lot in a minute here when we actually start coding. Okay, so everybody understand a little bit about hexadecimal enough to at least not panic when you see the 0x in front of your digits. That just means that it's a hex address. Okay, and when we talk about pointer arithmetic, it's important that we know that those are hex addresses so we don't get confused, because what this is all going to lead down to is like you're going to have something like, you know, 108, and suppose you're trying to reach 120, that address, and you might be like, oh, that's easy, all I gotta do is add well, that's too big of a gap, let's just do 110, you know, that's easy, I'm just gonna add 2 to that. No, because if this is hexadecimal, which we'll see because you have symbols in front of that, then that actually is an increase of not 2 but 8. That's how you get from 108 to 110. You have to add 8 digits to that, you know? So hex math versus decimal math can be a little bit tricky if it's your first time around in the rodeo of that. So yeah. So I will review that when we did pointer arithmetic, but it is indeed easy once you know what's happening. But before that, it looks like some magic. So I think now we are ready to do code. Okay, so a pointer variable, I defined it as being a variable that can keep an address. Okay, and it's a memory address, which, as we said, is going to be in hexadecimal. Okay, however, the system is still storing things in binary, so it'll still, even though it's a hexadecimal address, it's still being stored with a bunch of zeros and ones because that's all the computer has. Okay, but it's represented as a hexadecimal when we go ahead and print it out. Now, what does this address represent that the variable keeps? Well, it can represent some other variable or somewhere else in memory that is storing data. So it's basically like saying, inside of this variable, which has its own address, by the way, we're going to keep the address of something else. Now, why would you do that? Because you might want to remember when you store something else. So you're keeping an address to that location in memory. Furthermore, when we learn about dynamic variable allocation, that is going to be mission critical to not lose our variables and create what are known as memory leaks. And so, in addition to understanding a pointer variable, let me go ahead and define to you 2 new operators in C++. Okay? And that is going to be, well, one of them you've seen already, but I'm going to define to you another functionality of it. So far, you know, if you have a variable A and a variable B, and you can define these variables to have something in it, like A and 2 will be, you can say something like A equals A times B, right? And we know that in C++, that little asterisk there happens to mean the multiplication symbol in C++. Right? Well, now we're going to give it another definition, and that is known as the dereference operator. So that is spelled as following. I'll put it in here. Okay? In fact, here, I'll just write it here. So the asterisks, and I always mess up my asterisks when I'm writing them. Like I do this, but I don't think that's the way they're done here. They just do it like this. But I guarantee you will see me doing them like this, okay? But technically that's the right way. I guess I do one too many lines, okay? Yeah, looking at it's the number beneath the A. So this, while this is the multiplication symbol whenever you're using it as a binary operator with things like integers and decimals, when you're dealing with addresses or pointer variables, it's known as the dereference operator, and it's a unary operator, kind of like the pre and post increment. So let me see how you spell that, referencing. Okay, now what does there's another nickname for it. I don't really use his name. Indirection operator. They both mean the same thing, but that does add to the joke of saying there is no problem you can't solve by adding another level of indirection. And that's a popular joke in programming. And hopefully by the end of 202, you too will understand what the joke means. If not, probably by 302, I would say. So, yeah. The dereferencing operator is very, very, very powerful, because what we do is, if we have an address somewhere in some variable, and we dereference that address, what that does is it takes us to the location of the address. So, suppose that I have a variable A that has an address in memory, okay? That 100 is not 100 in decimal, it's 100 in hexadecimal, okay? Whatever that is, whatever that 100 represents in hex, okay? It's definitely bigger than the 100. If I go ahead and say asterisk A in my program, what's going to happen is I'm going to basically try to access whatever is stored in address 100 and try to print that out. Okay? So in memory, you have something called a stack and a heap, and that's part of your RAM. And you can think of them as growing structures from both ends of memory. Doesn't matter which one you put on the top and the bottom, but you can consider this to be the stack, and you can consider this to be the heap. And what happens is, as you add data, they grow this way and this way. And the reason they grow this way is because if I have a program that's very stack intensive, you could have the stack take over most of this, and then the heap uses a little bit. Or vice versa. If a program uses the heap a lot, you know, you have this growing very much and you have this very little, okay? Regardless, when you're looking at a variable, if you dynamically allocate it, it's going to go in the heap. But if you are just declaring it in your program and it gets compiled, it's going to be in the stack. So for now, you know, if we zoom in on the stack, there's going to be a lot of addresses, and they're going to be contiguous. And so on, okay, until you get to address 111, and so on until you get to like address 999 or whatever. Okay, actually the biggest address here, if we're doing 3 digits, would be FFF. Okay, so suppose that I declare variable A on the stack, you know, so and then the compiler basically gives me somewhere in memory, and so the compiler is going to say variable A has been granted usage of this square, okay? And in that variable, I am storing address 100. So I'm storing this value, okay? So what happens is, when I dereference it, so when I do star A like that, I am saying, look at this and actually go to address 100. So that means go up here. And suppose that there's other data here. Maybe there's a 5 here, a 2, a 1, some garbage, garbage, blah, 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 whatever. If I go ahead and say cout asterisk A, which is dereferencing A, that is basically going to go to address 100, which has a value of 5, and print out 5 out of that. Okay? So all you're keeping in A is an address of something else. Now, you don't even know that A is stored at address 103. That's something that the compiler decided. But what if you wanted to find out where something is stored? That you can use something that you've seen before already, and that's the ampersand, which is known as the address of operator. And that's kind of your complement when you're dealing with pointers. You have the dereference operator and you have the address of operator. Okay? This one's also a unary operator that, as the name implies, returns to you the address of whatever you're passing it with, what operand you're passing with, right? Because remember the rule, you have operators and you have operands, you know? So when you have an addition thing, you have operand plus operand, and the plus is actually going to be an operator. So when you have a binary operator, you have something of this format. Operand, operator, operand. This could be a plus, this could be a minus, multiplication, even division, right? And this could be a number, and this could be a number as well. When you're dealing with a unary operator, you could either have something like this, operand, operator, or you could have operator, operand, right? An example of this would be something like a plus plus. That's technically a unary operator. And something here could be like -5. That would be a unary operator as well. Okay? With the dereference operator, that becomes something like that. I have a variable and the dereference. For the unary, similar thing. You can do ampersand and then the variable name. And what that's going to do is that's going to return to you the address of that variable. That's going to be the hexadecimal address of the variable. Okay? So it returns the address of its operand. And for the dereference operator, I guess I'll put the formal definition, which is refers to the object to which its operand points. And the operand is going to be the address loop, the variable containing an address. Which another nickname for a variable containing an address is climatic pause pointer. So that's what a pointer is. It's just a variable that has an address, which now you know how to get. So now let's try it out. So, how do you declare a pointer variable? The syntax is going to be data type, dereferencing operator, and an identifier. An example of that would be an integer pointer. This has created a pointer variable. Now, I think this is going to work really cool, actually. Let's use the other thing that I had before. Yeah, so remember the thing where I have the side? So, cool. So what I'm going to do is, even though I don't know the exact addresses in memory, I'm going to pretend I do so that you can kind of see it. And then we'll see the actual running of this, okay? So, right now, where is that in the picture? I need to draw like a line so I can see where it is. So that is like, okay, so that's right at the beginning, and then it ends here. Okay, so this is my area of basically where I can draw it. Cool. Okay, I needed to make sure that, so that I don't write off the screen. Okay, come on. I'm trying to erase everything that I did. Okay, so see if I got this right. I can do that. Failed. Oh my gosh. There we go. Okay. So I have my stack here, and just so you can see, I'm going to declare another variable. I'm going to call that one B, and I'm going to store 20 in it. Okay. So when this program is being compiled, and when it it's compiled, and when it runs, I have my memory, and I don't have control over this, by the way. This is something that the operating system will handle for me, and that is, it's going to assign somewhere in memory, and in my memory, let me move this a little bit, maybe here. This is kept with hex addresses. They can be anything, okay? However, it turns out that typically in memory, you 9 A B C 10 C. Typically, the addresses are stored as by multiples of 4. Okay, that's just that's a computer organization thing that you will learn when you take CS 219, or actually no, 218. You'll learn that in 218, but if not in 219, you'll learn it too. So even though I've been saying your addresses are increasing by 1, it just happens to be that they are kept in multiples of 4, because you can think of it like in terms of land, each of the squares can hold 4 bytes. And technically, if I was to access address 0, 1, 0, 0, 1, 2, any zeros there, 2 here, that would actually be, of the 4 bytes, you can think of this as being split into 4 pieces. This is technically address 100, 101, 102, and 103. So that would be actually this address right here. But most of the data types that we have happen to take 4 bytes. Which ones take less than that? Technically, a car should take less than 4 bytes. It should just take, I believe, just 1 byte. However, in modern computers, it's not a good idea to put multiple data within the same word or the same line here, and so they just fill the rest with nothing. It's a waste of space, but it's just easier for the organization of the system. I don't believe that it will actually try to squish things together like that. Most of the time, it just if it takes less than 4 bytes to store whatever we're storing, it'll just give you 4 bytes. It's like the smallest amount of space you can rent is a little PO box, and the PO box takes 4 squares. So you can't, if you want to use 1, too bad, you get 4. So just waste the other ones. Okay, that's kind of the idea. Okay, so we'll say that somewhere way down later in memory, we got address 0300, which again, I'm saying 300, but it's in hex, so that's not really 300. You know what I'm saying. 1, 2, 3, 4, and then 0x308, and so on. Okay, this goes on for a long, and it also goes on upwards. So when I run my program, let's just say that B gets allocated. Again, we have no control over this. So all of a sudden, it just decided to give us this spot right here, okay? When we get that piece of memory, we are initializing it to 20. Okay? Now, how is that 20 kept? It's kept in binary, okay? I think we did 20 earlier here for the binary, and you guys said something like 1, was it 10100? I think that's what you guys said. Let's see. 10100. Okay, cool. Yeah, so that was it. So that's how it's kept. Now, again, the rest of this is a bunch of zeros essentially, because you got 32 of these in here. So really, if you really want to know what this really looks like, is you got 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. 32. I think that's 32. I might have put one extra or one too few. I don't know, but you get the idea. I can't even fit it here. It's so big. Let's just shrink this. Whoa! It like transcended to another dimension there. So yes, they're all the same size, but In fact, oh yeah, I forgot you can't even see the rest of that. So I gotta shrink this even further. So yeah, okay. There's your 20 in binary. So just kept as that, okay. But I'm gonna represent it as just a 20, okay. You just have to imagine the binary part. So, that you're wasting your points on that. That means you're not using your points in the extra credit. But anyways, yeah. So okay. Next in our program, we are creating a pointer variable. That pointer variable has to be stored somewhere as well, just like B, and it's also on the stack. So it doesn't have to be contiguous. It could be anywhere else. More than likely, though, it's probably going to be right next to it, but it doesn't have to be. You have no control over that either. So we'll just say that, you know, it did get put next to it. So that's going to be put here, okay? Now, what is stored there? Who knows? There's a bunch of zeros and ones in there, 32 of them actually. Whatever was used last time. So it's just garbage right now, okay? That's okay. Cool. All right. Next, why don't we go ahead and make our pointer point somewhere that it's valid. Now, we could do this. I could in theory do this, although we will talk later what the limitations are. This is allowed, but you have to use a permissive, and you really shouldn't. I could make my pointer variable have a direct hex address. Like I could do something like this, okay? However, that's a horrible thing to do, okay? Don't ever try to hard code these addresses because they will change every time you run them. So, and you would have to use something called f permissive anyways to even try to assign something to it. So, don't do that, but know it's possible to do. Unless you really have a reason why, and you're like a master at pointers, then you don't want to mess with that. But something better that we can do is, we can use the address of operator, because suppose that I said right now, cout $b, okay? What would that line of code do? What that line of code do is it would print out to the screen the address of b. What's the address of b? You guys tell me, what's the address of b right now in our little thing here? Chat, what is the address of b? 0x108. That is absolutely correct. Yes. Good job. All right. Cool. So I'm glad you got. I want to make sure you guys were following. So yes. Okay. So yes, the address of b is 0x108, which is in hexadecimal. So that's what this would print out. Okay. So this is a pointer, and it can keep addresses. If I wanted to point or keep the address of b, I can use the same syntax of the $b and do something like this. What this is going to do is it's going to store in A, which A is currently residing in 100Z, and it's going to remove the garbage and going to overwrite the garbage with the address of B, which happens to be, as you guys all eloquently put it, 108. Okay? So that's what it's storing. That's what it's physically storing. It's storing the hexadecimal value. Well, again, it's in binary, but it's storing the hexadecimal value equivalent of address 108. Cool. Furthermore, if I try to say cout, well, first of all, if I try to say cout b, we can all agree that that's going to go ahead and print out 20, right? That one's easy. We've done this before. But what if I try to do cout a? A is a pointer. All it contains is an address. If I do cout a, that is going to print out 0x, in my little example here, 10c, okay? Which happens to be the same address of b. That's the address of b. Furthermore, if I do the dereference operator a, like that, what do you think that's going to print? Well, the dereference operator is going to tell us what is in the address that we're holding. So what it's going to do is it's going to look at the 108, and it's going to go to that address, which happens to be right here, and it's going to tell me what's there. So that line is actually going to print out 20. Gets even cooler than that. Suppose that I do asterisk A, so dereference operator A, and assign a value of 30 to that. Okay? If I do that, what's going to happen is it's not going to try to replace the green square, or sorry, the blue square. It's actually going to replace the green square, because what's going to happen is it's going to dereference A, which means it's going to go to wherever A is pointing, which is address 108, and then it's going to change that value. So what's actually going to end up happening is the 20 is going to get replaced by an 8. Or, sorry, why did I say 8? 30, not 8. Sorry. Okay? So, as a final experiment here, if we try to see out B again, which before was 20, now, what do you think this will print out? Chat. 30. That's correct. Yes, it will print out 30. Yes. And so you have indirectly changed a variable, because we never actually change. You never have a b equals part here. There's no b equals. If I had done b equals something, then we change it. So we use the pointer to change a different variable. And that's a very, very, very powerful thing that we have achieved here. Okay, cool. So this was our toy example. Let's try to run it now and see the actual addresses, that we would see when we run the program. These are, of course, going to be different because I have no control of where things are getting assigned. But I suppose one last thing before we run it, because it will be interesting in our purposes to see. Let's actually see where B is stored. Yeah, oh no, we do see it. So we see where B is stored. We see where A is stored. Perfect. Okay, cool. So that way we can see all the addresses. Okay, so I compiled, and when we run it, bam, you can see this is the hexadecimal address that is currently where B is stored. Okay, so B is stored right here. Oh, I guess before here, that's what I meant when I wanted to add. Let's actually see where A is stored before. Oh no, we do print it out. See out A. Ah, yeah. Okay. Yes. So let's actually print out here, in addition to this, let's print out ampersand A, okay? So this one's a little bit weird. This one is going to print out the address of A. So that should print out 0x10c, okay? That's going to be the address of where the A variable is kept in the stack. Not where it's pointing to, but just where it's kept. It might be also cool to see that. So, okay, we added that in. Let's run it again. Yeah, so this is kind of cool. Okay, so let's go through these because I didn't label them exactly. So the first one here is coming out of the C out here. So that is the address of where B is stored. By the way, notice that when I ran it before and when I ran it now, it was different each time. That's to be expected. That's because we have no control over where the operating system is allocating memory for our B variable. If I run it again, odds are I'm going to get a different variable. As you can see, I did. In fact, I'd be almost winning the lottery to get the same location in memory. This is in main memory in RAM where it's being stored, okay? Okay, so that's this one. The 20 is, of course, just couting what's contained here. So in this address, at the time of running the program, 20 was stored there, and I got it printed out. Next, we are seeing, next we go ahead and we assign A to store the address of B, and then we go ahead and print out what's stored in A. As you can see, it's just storing a hexadecimal value. So whereas this is the address of the variable by printing ampersand B, this is literally printing out what A currently contains. So this will be our 0x108. That would be the blue square would be this. As you can see, it's identical to the address here, which is kind of matching what I have where I have right here. So this address is the one that ends with C1C, okay? Which is also matching the 108 there, okay? Cool. So from there, we move on to this is the one that I added. So this one right here is the ampersand A. This is actually where A lives. So this is the address 0x10c. That would be that address here. So I'll highlight it and then delete it so you know where I'm pointing to. So let me use a different color. So this one right here, this address right there, That one is our 20 address. That's where A is actually kept. Notice that I was right in my sort of guess that it actually is keeping both variables next to each other in main memory. Again, it didn't have to do that, but it did. Why did it do that? Because we declared it basically one after the other. And so, you know, when you talk about locality of reference and those kind of things, this is actually a useful feature to have. If I was to throw in a random variable in between here, you would see that this would shift over a little bit. So as you can see now, the addresses are very similar, but there's actually a difference of, is there still the same by one? It goes from C to, oh yeah, it's still the same. So well, maybe because I didn't store anything in it. So basically the compiler is like, that's a useless variable, I'm deleting it from your program. Yeah, see, the compiler is a little bit smart. It's pretty smart. So even though I have a variable here declared, it's like, yeah, you're not using that variable, so we're not even going to create it in memory. It actually, I think it went ahead and did that. But now that I actually put data in it, it was like, okay, fine, we'll make it. So now you can see that the difference went from only 4 bytes here, because again, this is the hex. This C, you know, you add, it becomes D, that's 1 byte, E, 2 bytes, F, 3 bytes, and then 0, 4 bytes. So then that's why it goes from 9C to A0. Whereas here, because I threw in a variable in between my X and the B and A declaration, now there's 8 byte separation there, because it goes from 8, so it goes 9, 1 byte, 0, 2 bytes, A, 3 bytes, and B would be 4 bytes. Did I get that right? 9, no, apologies, I said 0, that's why. 0 is at the beginning, so it goes 9, A, B, C. There we go. So C. So C is where variable X is stored, but since we're dealing with A, it also adds more to that. So it goes D, E, F, and then 0. So that's why you see a difference of 8 here versus a 4. Now the question says, can you explain the difference when you see out A and asterisk A? Yes. So couting A is couting with the contents of A. A is our pointer variable, and it contains, pointers always contain addresses. So when you see out A, we are printing out an address, which is what's stored in that. So that would be the 108 in our example here. That would be the contents of just couting A. Whereas couting asterisk A is dereferencing that address. So it's saying, go to the address that we have stored here. So go to address 108 and print out what's there, which in this case is 30. In the case of the program, the address here, 60, is actually what A is. So cout A is printing that out. That's the address of where A lives. So couting A, sorry, no, apologies, my bad. This is coming up from the ampersand A. So couting A is going to print out the address of B because we copied it into it. But it will print out whatever address we have there. And then dereferencing it is printing out the contents. That is when we see the 20 being printed out. So asterisk A will print out the contents of what we are pointing to. Okay? So I'll say that again. Asterisk A, also known as dereferencing A, or indirect adding or giving the indirection of A, is going to print out the contents of what A is pointing to. Now, what is A? What is in A? What is the address in A? That's what you get when you just cout A. So couting A is going to give us the 108. Couting star A is going to give us the 30, because that's what the A is pointing to. If A was pointing to a different address, so let's say that A was pointing to address 110, then cout A would say 110. And then asterisk A would print out whatever is in this square here, the one that's empty beneath. Okay? Does that make sense? So back to this again. This is coming out from your ampersand B, which is the address of B. This is cout B. This is cout A, because now we made A point to B. And then this is where A actually lives, so that would be our 10C. And then this is dereferencing A, so that's the 20. And then asterisk A equals 30 means dereferencing A, store something there. So in this case, we're overwriting B with the 30. Yes. Ampersand A points out to where A lives. So every variable needs to live somewhere. And the address of operator is going to give you the address of A. So address of A, which is going to be 10C, which is where A lives. So all variables live somewhere. Even if they're pointers, they have to live somewhere. It's like literally, if I'm pointing at someone like this, I have to live somewhere. And that's my address. Ampersand of A will give you my address. And then, if you want to see what I'm pointing to, then you can just see out A. And then if you want to see what is actually where I'm pointing at, then you can do the asterisk A, which is going to tell you where I'm pointing to and what's there over there. To make things harder, you can kind of make this a little bit more complicated by having a pointer point to a pointer that points to a pointer. So like, if I'm pointing here, and then I'm pointing to somebody that's pointing to something else, if I go ahead and say that, I'm going to get this address or this pointer. If I do this, then that's going to go to who he's pointing to and then who he's pointing to. So that's going to get me that guy. So you can have a pointer pointing to another pointer that points somewhere valid. Why would you do this? One reason would be to confuse people, but the other one is actually for a very useful purpose, which is when you're creating arrays. It's actually going to be very, very useful when we get to that. So there's a reason to do this, but as you can see, this is adding a level of indirection, which is adding another layer of pointers. So, so far so good. Ask questions now. If the third guy is pointing to the original guy, could you just have an infinite loop of asterisks? Yeah, so here, let's do that. I mean, not infinite loop of asterisks, but you would just basically add as many asterisks as you wanted, and you never get anywhere valid, I suppose. So let's just do that. Okay. So here, we'll just do it at the top. Put a return 0 here so we don't get a bunch of stuff printing out. So let's make a pointer A. So this is oh wait, we gotta use different variables. So we'll call this guy 1. The asterisk here, again, in this case, even though it's the dereference operator, it means that this is a pointer variable. By the way, what happens if I try to do this? I want to show you. Invalid conversion from integer to integer asterisk. What this means is I'm trying to assign a number to something that's supposed to hold an address. Okay? So it's basically like, that sounds like a really bad idea. However, I can totally do it. If I go ahead and do f permissive, it will compile. It just gives you a warning, but it will compile. And if I run it, in this case, it won't crash. However, if I try to dereference it and go to that address in memory, so that's address 10 in memory, which would be A in hexadecimal, that's going to be really bad. Probably going to crash or print out garbage. We'll see. I think it'll crash. Oh, guy 1. Crash. There we go. Segmentation fault. So hey, let me get rid of this so you can better see the chat. There we go. By the way, yeah, cool. Okay. So if when you're compiling you get a problem like this, don't just do the f permissive and crash it, because you're probably doing an actual more important error. It just means that your level of indirection is wrong. Okay. So next, I don't think you can do something like this. I think it'll give you an error, but let's try it. Ah, it worked fine. Cool. So could I try and guess the addresses of where they're at? Again, they're going to be different every time. So I could try. But I'm going to be wrong. But let's just see if I can get something to print out that's valid without it crashing. Let's try that and see what happens. No, still crashed. So pretty hard to do. Again, you don't want to do this because again, it's impossible for you really to figure this out. Unless you have a way of getting the address somehow, somewhere, then actually, I have an idea. And then we'll do the guy example in a second. Let's go ahead and let's create a variable. Little baby hack thing to do here. Let's go ahead and create a variable called objective, and let's store a 10 in there, okay? And then at the end of this, we're gonna see out objective, okay? Now we're gonna see out the address of objective at runtime, and then we're gonna read in from the user an integer. So we'll call this input. Okay? And then, now that we know that address, we're gonna make our pointer int guy, and then we're gonna assign to guy1 whatever we stored in input. Okay? Yeah. It's going to give us that warning. Again, this will never compile if you didn't do f-permissive. Let's run it. Okay, now we know their address. So we can actually manually type in that address. Okay, if we type something random here, we'll get a seg fault, okay? However, if we run it again, and this time, let's convert this number here, or here, I'll just type it, to decimal, and see what that would be. And let's store that in decimal. So 7FFC35E2AC14 to decimal, hexadecimal converter. Here we go. So enter a hex number. 7FFC35E2AC14. Oh no, that's too big of a number. We're gonna overflow this thing, I think. We might have to store it as a long integer or something, but we'll see. So the number is 140721212533780, and we segmentation faulted. Okay, let's store this. This actually, you know, could we do that? I don't know. Could we do something like guy1 here? We might get away with it. Otherwise, we can use a long integer, and then that'll do it for us. Oh, I see what's happening. It's converting it. It's converting it from decimal to binary, and I think that's screwing it up. Yeah, it doesn't like that either. Okay, so let's try unsigned long integer. And then input, and then we're going to assign input to that, and then we're going to see out guy. Okay. Expected semicolon. Okay, so let's convert this back to hex now. So we got 7FFC2EF78974. Convert. And so the number is 140721096460660. Oh crap, I'm not typing it. Damn it. Okay, apologies for that. So 140721096400660. Yes, I got it. Yay, cool. So I manually converted the hexadecimal value to an integer, a long unsigned integer. Now, why unsigned? Because by making it unsigned, I avoid that signed bit messing with my hex numbers when they get too big. Otherwise, it'll overflow and become a negative number, and that's probably what's causing some issues potentially. So, yeah, I know the dog. So, anyways, so we we can see that I can see out the 10, but I can also see out my pointer, and it's pointing to the 10. And not just that, but let's take it to the next level now. Now that I know this works, let's actually go ahead and do guy gets 9,000. Okay, and then guy 1, sorry, gets 9,000. And at the end of this, the last thing we're going to put in is see out objective, which hopefully we managed to quote unquote hack and change. Okay. Semicolon. What does long do when you put it in front of the integer? It allows you to keep a bigger number in there, so it's kind of avoiding me from going out. I think we don't actually need the long part. I think it just needed to be an unsigned, but it's just a bigger number system. It keeps it in 64-bit. I think the reason why is because my computer is running 64 addressing system, and because it's running 64-bit addressing system, an integer is only 32 bits, and so I kind of needed to make it a long, which should be 64 bits. So yeah, that's just kind of why I switched it to that. Just to show this example. 40D434. This is all going to depend if I actually copy the number right. So let's make sure I copied it right. So we got 140725027132468. Ah, shoot. Yes, there we go. We got it. Okay. So I converted this to hexadecimal using rapidtables.com, and then I go ahead and see out the value that we have, the 10, and then I changed the pointer manually with what the CN was right here. So I manually typed in the address, and then I go ahead and assign something to the address. So I changed the address from 10 to 9,000, and then I go ahead and print it out. So I quote unquote change my pointer on the run. Now, this would have never compiled without a permissive, because again, it's a really, really bad idea to do something like this, because the only time that you should ever do this is if you actually know the address at runtime. And the only way that you can get the address at runtime is in the variable time by using the address of operator, or if you're doing something like C and C out, it's because I actually looked at the address and manually typed it in. So that just shows you that the pointers are just addresses, and you can put in any address that you want in that variable, and it'll try to access it as a pointer address. Before I was crashing because I got the math wrong, but now it's working because I actually converted it right with the hexadecimal converter. Okay, so just a little bit of a demo of injecting code per se, and that's how basically an injector works. You know, they when you load up like a game, you know, those DLLs have memory have somewhere in RAM. They keep things in memory, like the position of the player and things like that. And then you load up an injector, which is going to find at runtime where that is kept in memory, because every time is different when the program runs, and it's going to get that data and or inject into the game movements, or extract information from the game, which you can then use to code a namebot and things like that. And that's how that works. Now the anti-cheats will detect those injectors because they're pretty generic. But yeah. So for that, you got to get around the whole memory protection services. So, because normally you wouldn't be able to do that, but yeah, basically that's what you're doing. Same thing. Anyways, that's another little demo. That was cool. I'll comment this out because I'm not going to be trying to do that every single time it runs with the addresses. But let's go back to the guy example now. So we got guy 1, which is a pointer. Right now it's not pointing to anybody. We got guy 2, which is also a pointer. And then we got guy 3, which is also a pointer. So first, we're going to make guy 1 point to guy 2. So guy 1 is going to get the value of the address of guy 2. Okay? And don't forget the, no, you don't need that for that one. Yeah. Yeah, okay, cool. Next, guy 2 is going to get the address of guy 3. Okay, finally, guy 3 is going to get the address. Well, first of all, let's just make it actually get an address to something valid. And then we'll go ahead and make them point to each other, okay? So we'll have a variable called y, which has the value of 22. Okay, so we'll say that guy 3 has the address of y. Okay, Now, so that we can see where each of the guys live, because they all live in somewhere, we'll see out guy 1, address of guy 1. So address of guy 1. Oh, I forgot to move this one up here. Feeling better, by the way. I think the pill is starting to work. We got guy 2 and guy 3. Okay? So, thanks. That's just going to print the addresses. So let's just run this and see the addresses of where these guys live. Cannot convert into, what's just an address that I'm getting from him. I see what it's doing and why it's doing it. It's just that I don't like it that it's doing it like this. This is the problem that we're going to solve with another level of indirection. But, oh well, I guess we'll do that. And then we'll do this one with 2 of them. Guy 2. I see what's happening. Yeah. Okay, there we go. So this is an example of how you the little joke I was saying. There's no problem you can't solve by adding another level of indirection, which is translating to say there's no problem you can't solve by adding more asterisks to this. So this is a double pointer and this is a triple pointer, although people don't really call them that way, but you can if you want. And so the reason why we have to do this nasty stuff is because this guy is not really, so here's the thing. When you create a pointer, no, you're not just saying it's a pointer. You're giving it what it's supposed to be pointing to, or where it will point to. So when I say int asterisk guy, I'm saying that I'm creating a pointer whose job is to point to an integer. And you can't make it point to other things, or you shouldn't at least. You can, but you shouldn't. So in this case, guy is not really pointing to an integer, because as we saw, it's going to be pointing to another guy pointing. So because of that, when we have, for example, guy 2, guy 2 is pointing to guy 3. And then guy 3 is pointing to an integer. And so because of that, I need to say that it's a pointer that's pointing to something else, so it's double. A pointer to a pointer that's pointing to an integer, which is okay like that. In this one, it's a pointer pointing to a pointer that's 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 pointing to an integer. Yeah, 3 of them, okay? So as you can see, it can get pretty nasty pretty quickly, okay? However, these addresses are just contiguous because all 3 are neighbors and they live happily together, okay? So shall we finish the circle here? Why not? I guess we'll do a guy 4 because I do want to show something about guy 3 in a minute. So we'll make guy 4, or gal 4, how about that? I guess that would be the female version of guy. I don't know, English. We'll say gal, we'll just call her gal. Gal is going to be pointing to guy 1. And guy 3, we can say is pointing to her, okay? And then we'll come back to guy 3 pointing to this. So we'll say that we'll come in this line out, and instead we'll say that guy 2 is pointing to gal. And gal is going to be pointing to guy 1. So that completes the circle. So we're going to do guy 1 pointing to guy 2, guy 2 pointing to gal, and gal pointing back to guy 1. Okay? So this. So we got, that's guy 1. Then we got guy 2. Then we got, that's supposed to be here, gal. And then gal is pointing to guy 1. Okay? So we got the circle. Oh shoot, you can't see that. Hold on. Let me move it. I guess we'll shrink it so you can see it. There we go. Okay? So you got guy 1 pointing to guy, or guy 1 pointing to guy 2, and then guy 2 pointing to gal, and gal pointing back to guy 1. Okay? So they're all blaming each other for something they did, I guess. And so gal has to get the address of guy 1. All right? So now we're going to have to mess with this to get it to compile. If it even compiles. So gal needs to have a lot of asterisk in front of it. Okay. No, wait. No, that's not gal. Guy. You're not convert. Ooh, okay. I don't know. Maybe. That's going to cause problems. And now that one has problems with guy 2 becoming to gal. So, also, we forgot a semicolon here. Okay, so then this needs 2 asterisks. But now it's going to complain that guy 1 needs 1 asterisk here. So I don't know if I'm going to be able to achieve this. Because it can't resolve that this is a pointer. They're basically asking for more and more pointers. So here, let's go back before we go any further here and screw this up. It will work fine if we made gal not point anywhere. So that will be okay there. But when we make gal point to the address of that, how about we do cannot convert a 4-way pointer into a single-way pointer. I understand why, but I'm just seeing if there's ways we could work around that. I can't think off the top of my head of one way to make her point back. Yes. Yeah, I do. But it actually never got to parsing that error because of the problem before it. That's why it didn't tell me that. But, it just made 1 more asterisk now. Could I make it point to that? Maybe if I do this. Okay, that made it worse. I don't think that will work either. So yeah, I'm not sure. I'm not even sure how I could do that. Like, I'm not 100% sure that I could even achieve that without doing bad things. Because that's some circular referencing that I'm trying to do here. So what I could do is I could do this, actually. Yeah, I could do that. And then I just have to change probably gal. So without an ampersand, I just need to add 2 asterisks there. I could probably do something like this. Okay, so then I can make this one be that. And now I just need 1 more. Could I do this like that? No. I can add 1 more to guy. And now I just need to fix the top one. Okay, so that compiled. I have no idea what this actually will do, but now they're all pointing to each other. Oh, I see. I kind of see. So I probably could have gotten away with just removing 2 levels of indirection from each one. I think that will still compile. Yeah. Okay. So I kind of was cheating around with doing the extra asterisk. So what exactly is happening when you have multiple dereference operators like that? We're saying that rather than getting the address of what you're pointing to, you're gonna get the address of what you're pointing to what that is pointing to. So we're going if I say asterisk guy 1, this is gonna give me whatever guy 1 is pointing to. So that is guy 2's address, or sorry, guy 2's value, which happens to be a pointer to gal. So that's actually, this would give me the address of gal, okay? 2 asterisks there would give me the address of whatever this is pointing to and what that is pointing to. So in this case, that'd be 1 here, two hops here, and then it would give me whatever this is. Make sure we get 1 dereference here, 2 dereferences here. Yes, so that would give me what is in gal, which would happen to be, I suppose, the address of guy 1 because we're pointing in circles, right? So yes, 3 asterisks would get me the address of guy 2, which is what is in guy 1, okay? And that's when we're going in circles already. So right now, the way that I have it, I have guy 1 equal, and that's not really what I'm achieving here in a way. In this case, what I'm really just achieving is they're all kind of pointing to each other, because if you can see here, guy 1 gets guy 2, and then guy 2 gets gal, but then gal gets guy 1. I suppose guy 2 is not pointing to guy 1, but they're identical because guy 1 happens to be guy 2. So it's a mess. You don't want to do that. You know, we're only doing this, I guess, for educational purposes, I suppose. But let me. Do you have any more questions about this mess of an example before we move on to more practical applications, we shall say? Don't try to point things. I mean, when we talk about linked lists, that'll come in useful. It is cool, yes, and it's good because it's good exercise for like really understanding pointers to do this weird stuff. So actually, we'll leave it all like this. So let me tell you what an actual real usage of a pointer is. Okay, so while it is useful to have what are known as aliases of other variables, so like if you have a variable a and you have a pointer b that points to variable a, it's cool because you can change both a or b, and neither of those would change the same location in memory, and that could be useful for implementing some algorithms. However, the real power of pointers, and really where we should start with pointers, is what is known as dynamic memory allocation. So that's going to be kind of like the big topic here. The real reason why we're really talking about pointers. Dynamic, oh, here, let me, so you can see dynamic memory allocation, okay? So, what is dynamic memory allocation? So far, as I showed you already with the loose stack and heap, all the variables that you have declared, minus maybe the vector stuff, are stored in the stack. And you know exactly how much space you need at compile time for this. That's why your arrays have to be a defined size, and why when you're passing parameters with arrays, you have to put in the size in the function parameter, and so on. All of this stuff, you knew exactly how much space you needed to run the program. So when you execute your program, the program knows that it needs to allocate, I don't know, 20 bytes Probably multiples of 4 though. So probably like 20. Well, hey, 20 is actually multiple of 4, yeah. So if you have 4 variables in your program, it's going to need 20. 5 variables in your program, it's going to need 20 bytes. You know, potentially. If in an ideal sense where nothing else was required. Not true because you have probably command arguments and you have some internal stuff, but approximately, okay? So at compile time, you know exactly how much space you need. However, if you need more space at runtime, you can't. You're limited as far as you know, except for vectors, again, because vectors was kind of cheating ahead. But if we ignore the concept of vectors, there is no way that you can add space at runtime with what you know so far, okay? If you were doing an assignment where you had to read from an array and you didn't know how much data you needed, then you were in trouble because you don't know how much big to declare the array. You try to make it really big and then just hope that it never fills up, you know, and then you'd be okay. But if it did, you're in trouble. That's why with assignment 1, we had to use a vector to cheat around that. But again, that vectors is cheating because it's actually using dynamic memory allocation. We just didn't know what it was, I suppose. So the question is, can I change the size of the space that I can use in the program at runtime? Can I allocate extra space if I need it? So if I'm reading a file and I need to read in 100 variables in there, but maybe next time I run the program I need to run in 1,000, it doesn't make sense to always allocate the maximum available size. It only makes sense to allocate how much you need. And to allocate it after you know how much you need. Because if you don't even know how much you need, you might be like, well, I think I need 1,000 because that's the biggest I need. But the next time you run it, you need 1,001. And now you run out of space. So dynamic variable allocation is going to allow you to, at runtime, so when your program is actively running, to create more space by asking the operating system like, hey man, can you like loan me out some space so I can run my program and then I'll give it back to you afterwards? I promise I'll give it back to you. And the operating system is like, yeah, sure, here's the space. Now here comes the issue. You're telling it like, hey, I promise I'm going to give it back to you. But it's on you. It's your responsibility to give it back when you don't need it. Now, if the program ends and you haven't given it back, then the OS will take it back. But until your program ends, you are hostage. You're holding that memory hostage. That can be very dangerous, as we will talk about with memory leaks probably next time. Okay? So, these dynamic variables that we're going to be creating are going to be stored on the heap side of things. So no longer on the stack, but on the heap. Now, I believe the book has a nice definition on the dynamic variable, so I'm going to go ahead and pull that up and put that in. Dynamic variables. So page 830, at least in the version that I have. So variables that are created during program execution. That's not as nice as I thought it would be. Either way, I think I'm gonna take a journey to UNLV on Thursday this week and get my notes for 202 because all my notes are at UNLV for the class because I didn't know I was gonna teach it. I had this really cool example on pointers in there too, so you won't get to see that one, but you get to see my other ones. So I'll give you guys some intel on what UNLV looks like. Okay, so variables that are, I forgot the word that are created during program execution, okay? Now, how do you create these variables? With the help of pointers. So, pointers are critical to create these variables. You cannot make a dynamically allocated variable without pointers. Simple as that. If you are doing it, such as probably with vector stuff, it's because you're just calling a library that is doing the dirty work for you. But the dirty work is going to happen regardless. Okay? So, to allocate these dynamically allocated variables, you're going to need to learn about two new operators. Pun intended, because the operator is called new. Or one of them is. There's also, I'll skip ahead and put it in here so I don't forget. There's an operator called delete. Because he who giveth taketh away, right? So you are able to ask the operating system for memory to create these variables, but you should also know that when you're done using this memory, you should give it back to the operating system. And so that's why we need to know about delete. But I don't think we will get to delete today. But anyways, so how do you use the new operator? Well, there's two different syntaxes for it. One of them is for arrays and one of them is for integers. So I'm going to go ahead and put them both here for now and then explain them. So you put the keyword new. It's just it's just a C++ keyword. And then you put the data type that you wish to create. And then your semicolon. And that's going to be for a single dynamically allocated variable. However, if you wish to create a dynamically allocated array of variables, then you can go ahead and put this integer expression in here, which is just like an array, you know, like A5 or something, okay? So this creates a dynamically allocated variable. However, if I go in and just type that in like that, you know, I say new integer, and then compile and run this. Actually, I'm assuming it will compile, but yeah, I run it, and I'm like, okay, big deal, great. Okay, I created a dynamic allocated variable. How do I access it? Like, how do I actually store things in this great new variable I made? Because this is literally like you going to the leasing office of an apartment complex and being like, hey, can I lease an apartment? And they're like, okay, you leased it. And now I'm like, cool. Where's my apartment? Like, what's the room number? Do you have keys or like what? So that's where your pointer is going to be useful, because what is pointers for? Keeping an address, right? So that is going to be the address so that we know where we just leased the apartment from. Otherwise, we wouldn't know where it's at. Right now, even though we did lease it, we just threw away the address because new returns something. When you run this command, this new integer, it returns something. In fact, I've never actually done this in my life, but I'm assuming this will work. I'm actually kind of curious if this will just print out an address. Yeah, it does, huh? I'm surprised I've never ever tried doing that in my life, at least that I remember. But now I have. So this is just dumb to do, that's why. But I suppose what this program does, this little program, is it allocates an integer, and because new returns an address, we are couting the address. But then we don't do anything with it. We just count the address. So you can see that new does count an address. However, if we don't store that address somewhere, it's gone. Once new tells you the address, it's like it's a tell once, that's it. It's like he doesn't repeat things twice. You know, he just says it once, and if you save that somewhere, good for you. If you don't, too bad. You already paid the rent. you got it. You just don't know where it's at. So, you know, to the rescue comes in our pointer variables. We have an nptr, right? I'm gonna comment that out. I don't think I've never done that line of code, so I kind of want to save it for eternity here. So I'm going to create a pointer variable. In fact, here I'll do this in 2 lines. I create a pointer variable, and next thing is I'm going to assign that pointer variable to keep the address that new integer returns. Okay? Now I'm going to compile this and nothing's going to happen. But internally, I can now go ahead and cout ptr as many times as I want. And you can see that they all have the same address. Notice, by the way, that the address is also similar, but at the same time, it's very different than this kind of address. You see that? That's because that's a heap address, and the other one is a stack address. So they're both hexadecimal, but it's just a completely different spot in the actual physical memory. So that's why they look very different. By the way, if you're curious, like where does pointer live? Because pointer lives in an address as well, right? So we can figure that out by saying ampersand PTR. Like where does pointer live? Pointer lives in the stack, which has a stack looking address. And these look like heap looking addresses. See that? They look different. It's a useful thing to kind of recognize that when you're debugging. So new uses the heap then. I was noticing the address was yeah. So basically what I said, yeah. So new lives in new, not just new, but dynamically allocated variables, which is what new gives you. They live in the heap, so the addresses will look a little bit different. They're still in hexadecimal, but the number itself will be different. If I throw in that in my hex converter, you know, these addresses in decimal were giving me like billions, right? 1 billion, I think this was, or 14 billion. Let me see the number of zeros. Okay, too much effort. I'm just gonna copy paste it. That was the address that we last used. So whatever that is, I think that's billions. This latest address is 208CC20, which is in the millions, I think. Yeah, it's 34 million something. So very different location in memory, right? And again, it's RNG almost in a sense because we're gonna get a different thing every time. So I mean, they still look like, look, even though it's RNG, they still look like hex, you know, they look hex, well, they are hexadecimal, but I'm saying, you know, the heap ones look very different than the stack one, okay? So anyways, cool, we have allocated this pointer variable. We are printing out the address, we still haven't got it used yet. So let's go ahead and use it. That's gonna be the last thing we do today. Let's go ahead and actually store something in our brand new apartment here. What are we gonna store? 999, because. Okay, so we stored it, and I guess last thing we should do is let's try to print it out so that we can see that we actually successfully stored it. Again, pointer PTR is a pointer, so to store something where it's pointing to, so which is where the integer exists, we use the dereference operator. So the asterisk PTR is saying go to address, what was it, 20CCC or whatever, go to this address, and then there store the 999, because that's where that's the heap address that we want. And then this is basically saying go to that address and printing it out again. So here we got, this is where PTR lives. PTR has an address too. And then this is the address that we got. Again, we printed it 3 times. So this is the address that we've been assigned by the operating system as in where our integer is gonna live. And then we go ahead and we assign it to PTR by saying, we assign 999 to PTR by saying Dereference Operator PTR, and then we go ahead and see out it. So as you can see there, we are storing in this dynamically allocated variable the value 999, and our way to access and modify it is by using the pointer and using the dereference operator. Finally, even though I'll talk about it actually next time, but I feel bad about doing this, I am holding hostage the memory at that point in time. So if I want to release it, I would just do delete PTR. And nothing happens here, but as I'll show you next time, there is a program called Valgrind, which checks for memory leaks. I don't have Valgrind installed? Are you kidding me? Oh, I see. No, that's slash, that's why. ./a.out. Look at this. It says no memory leaks, right? If I remove the delete and I run this again, while I compile and run it, it says leak summary. So I'll leave you with the cliffhanger of like, what were these memory leaks and how are they going to make my life miserable when I'm doing homework? And enjoy your non-memory leak days, because now things will get harder in 202, because you will have to, this would lose you points in your assignment. So this will be your future. So we'll leave it at that. I went a lot slower than I expected today. I honestly thought I would get through delete at least, but life happens, I suppose. But don't worry, we're still with plenty of time to go. So we will talk about memory leaks, and we'll talk about delete and dangling pointers and all the other stuff that I usually teach when I'm doing pointers. tomorrow, which I'm sure I will be feeling better. Okay. What is the command again to check for memory leaks? It's valgrind. And then you put the name of the executable. So, but we'll talk about it. We'll actually go into detail tomorrow. Like I just wanted to tease you, but delete and valgrind and more practice with new. And we'll also look at malloc and free, which are the C version of that, because I like covering that. I think that's a useful. It helps you better understand allocation. So we will go into way more detail tomorrow about this. Now we got a question. Can you use a pointer to store a class and then use delete to activate the destructor early? Yes, you can, but be careful about doing this kind of thing. When you call delete on a class pointer, it will call the destructor. So yes, that will be the end game. That we will be using this for classes as well. That will be one of your bigger assignments too. So yes, there's a lot to come. Sorry I didn't get through more today, but you know, we got through some stuff. So let me know if you guys have any questions, and if not, then I shall see you guys tomorrow. Thanks for hanging in there. Any other questions before we end the broadcast? No problem. I shall make the first pointer assignment available if I haven't already. It's an easy one to kind of get you warmed up to it. No pup. Yesterday the pup came right after the end of it, by the way. I even took a picture. I made it the logo for yesterday's video. Is it up? Okay, cool. That's the one with Padme in it then. Yeah, cool. So you can start messing around with that assignment now with the pointer stuff. It's like a tutorial-ish assignment where I just guide you through every single line of code. I had a question for assignment 3. For enum first and last name, how are we supposed to change the integer to a string? With a function. You write a function that you hard code that. Like 1 becomes the name, whatever the name is, I think John or whatever, and 2 becomes Smith, and so on. So you hard code that, and you're gonna make these big functions that have a bunch of names on them. I think I make one of them for you in the skeleton code. I make one of them, and you gotta make the other one. Like I make first name and you make last name. I think that's how I did it. So just take a look at the skeleton code for an example of that. I believe you do, yes. Just like I did for the first name, you do it for the last name, or vice versa. I can't remember which one I did, but I did one of them. Just look at the other one. It's basically almost the identical code. It's just instead of first name, it'll be last name. So yeah, cool. All right then. I shall go and get some food. So I'll see you guys tomorrow, or I'll talk to you guys in Discord later if you guys have more questions. So thanks.